Okay, hi everybody. So what we're going to look at today is we're going to figure out even further how do particle accelerators work, and we're going to then analyze a specific particle accelerator to figure out what is the magnetic field within that particle accelerator and kind of, hey, how does it work? Which way is the magnetic field pointing? Why? So we're going to look at all that, and then at the end I'll kind of give you a old AP free response question that kind of summarizes a lot of what we've done with magnetism. So I'll try to post video solutions to all those, and then I'll just kind of have you, once you finish, check your work against mine. But so what we want to start off with is, in the past, we talked a little bit about particle accelerators back when we were doing our electric field studies. And we said, and like kind of potential too, right? So this right here is a graph of potential versus distance. And what we said before was in order to accelerate these particles to really big speeds, we have electric fields that are both pulling on and then pushing our proton while it's moving. So we see we're kind of spitting out these protons. They're attracted to the negative, then we switch that to a positive charge, and then it will be repelled by it. And that keeps on happening, keeps on happening, keeps on happening, and then we're able to accelerate our particles to great speeds. And really our whole entire point of these particle accelerators is we want to smash these particles into each other. In the Tevatron's case, what we're going to be looking at today is they smash protons into each other, and they want to smash them into each other. And then I think we looked at that video before, but then kind of trace out, using conservation of momentum, all these bits and all of these pieces that they get. And then based on an analysis of that, they can say, hey, we think of protons as these base units of atoms, but really we have these other fundamental particles. So they're really trying to figure out, what is this universe made out of? What are protons made out of? What are electrons made out of? What are neutrons made out of? So smashing these together at high speeds, using conservation of momentum then to analyze what the mass of these particles that comes off is once we collide these two particles. So it's really cool because it's kind of taking physics ideas that we've done and then applying them to a more, I guess, complicated situation. So the actual particle accelerators themselves, they are circular. They're these circular paths, like what's in this image here. So we kind of have this red one, and we have this blue particle that are going to smash into each other. I don't think they do in this GIF. But so they're going to smash into each other, and they're going to collide, and then make that little explosion. And it's kind of weird that it seems circular, because really what we need is this linear collision between them. We need them to hit each other. And I was doing a little bit of research online about why these things are circular, and really the main reason that I could find was we're accelerating these particles really, really close to the speed of light. They need a lot of energy in order for this collision to actually happen and tell us something. Well, I guess for them to collide and then break down. But so they need to travel really, really close to the speed of light. They need a lot of energy. So if we were going to be doing that in a linear collider, somebody said, I think on the internet I saw, like, it would have to be about the length of here to the moon. It would have to be a really long length for them to reach that same speed. But if we're doing it circularly, if we have this circular motion, we can accelerate these to even greater speeds without having to take up that much space. So if we're thinking about space and we're looking at this Tevatron at Fermilab, I just pulled a few quick things from it. I'll switch to this view so y'all can see it. But so here's the accelerator at Fermilab, and then a few little things. Oh, my mouse isn't going. There we go. So it says it was one of the most powerful particle accelerators, and accelerated beams of protons to 99.999954% the speed of light, which is crazy. We have a 4-mile circumference, lots of detectors. I really have all these pieces below that are making it run. Just kind of showing, hey, they're spinning around, moving, they're shooting out then. It's kind of cool. One thing that I really like, so here's kind of a above view of it, kind of an isometric view. If you look on Google Maps, you can physically see that this thing is massive. You can see these tubes that the protons are running through. So it's kind of crazy. It's kind of wild. So what we're going to do is, let me shift it back to me. So what we're going to do is we want to figure out, because it's kind of an interesting idea, well, number one, I guess it's, well, you'll figure it out. It'll be the first question on that form. But so the magnetic field is going to be what's allowing these particles to have circular motion, like we saw in that television question. these particles are, when they interact with the magnetic field, they curve. They have a circular path. So you'll see, number one, yes, we have a magnetic field. What direction is it pointing? Then I want to know what's kind of interesting is what's the actual magnetic field strength inside of this Tevatron? It's probably thinking, wait, it's probably pretty big. Like, what is this field strength? So we're going to be able to actually figure that out based on the analysis of items on that website. Excuse me. So we'll figure it out, and then we'll get an answer that seems a little weird, and then we'll kind of discuss this. Check back in here. There will be another video. So we'll discuss it, and then we'll say, hey, this answer is a little bit odd. Why is that? What is actually happening here? So we'll look at that, and then I'll hit you with one more free response question. But yeah, so try out this Google form now. Give it your best shot, and then we will discuss the answers in the next one. All right.